Students, in this second video, I am providing the virtual lab for the experiment Hall effect. For this one, first of all, we have to know what is meant by this Hall effect. It states that if we place a current carrying conductor or semiconductor in a transverse magnetic field, it is going to develop a potential perpendicular to both current and magnetic field. Okay, and that developed potential is called as Hall potential, and the effect is called as Hall effect. It is used to this effect is also used to find or measure the magnetic field, because we are not having any instruments to do so. Okay, and it is a connection between this magnetic field and current, or it is a device, or it is a principle that provides magnetic sensors. Okay, now based on this one, the force experienced by the charged particle in electric field is given by F is equal to Q into EH. Okay, or the force on the Q charge in E electric field, which is given by Hall effect. Then magnetic force on the charged particle F is equal to BQB. Then equating these two forces, that is at equilibrium, these two are equal, we can write EH is equal to BB. Then we write BH is equal to B into V into H, because electric field is nothing but voltage by distance, or in this case this is the height. Okay, and also we know current density J is equal to NeV. Then writing that current density in current, that is current per unit area, here area becomes T into height, where T is the thickness through which these magnetic lines of force are traveling, and H is the potential difference between the opposite points, and it gives the TH gives the area through which current I is passing. Okay, then if we simplify those equations, we get VH is equal to B into I into H by NE into TH into V, and writing 1 by NE or RH as RH, we get RH is equal to 1 by NE is equal to VHT by B into I, where T is the thickness through which these magnetic lines of force are passing through the material. Okay, then from this formula we can find the Hall coefficient. Okay, in our experiment we are going to find the Hall coefficient for germanium. Okay, by using this formula. For this one, we go to, that is we are going to do the experiment in a simulation way. First, go to Google Chrome browser and type Hall effect. Is there Hall effect simulation experiment? Hall effect simulation experiment. Okay, this is Hall effect simulation experiment. There we get Hall effect experiment. Again, it is given by virtual labs. Directly it will bring to this site, and we have to click on first simulate. Then here in this one, first we have to measure the magnetic field which we are applying. Okay, and for that one we have to choose this one, that is magnetic field versus current. Insert the probe, that is this is the probe which is going to measure the magnetic field. Then we have to click on this wooden box so that the probe is inserted between these two magnetic poles. It is reading 0.1482. You have to note down that reading. Throughout the experiment we are going to keep this magnetic field constant. Okay, then we come back to this one and we choose this Hall effect setup. Okay, here instead of having that probe, magnetic probe, we have to place our test material. Okay, then insert Hall probe. This is our test material. Then if you click on this wooden box, it will be inserted between these magnetic poles where there is a field of the last thing which we kept there, 0.14 something like that. Okay, then we choose this current, that is we should not disturb this current because this is the current that is providing us the magnetic field. Then we select the material. In the default it is given as germanium. Okay, we are going to find the Hall coefficient for germanium and we are taking the thickness of the germanium strip as 0.1 millimeter and we are sending this much of current, that is Hall current, 1 millimeter. Okay, then here we have to note down these values. Please take a note and make two columns. And before that one, you have to note this magnetic field and the thickness of the material. Okay. Now you have to make two columns. The first column is Hall current. The second column is Hall voltage. Hall current we measure in milliamperes and Hall voltage we measure in millivolts. Okay. Then first for 1 milliampere of current, the voltage is 28.756. Okay, we have to note down this one. Okay, 28.756. Then we increase this one Hall current in steps of 0.5 milliamperes. Next one is 1.5 milliampere. For 1.5 milliampere of current, the voltage is 43.133. 43.133. Then we increase this one 2. For 2 milliampere current, 57.511. 57.511. For 2.5, it is 71.889. Okay, 71.889. For 3, it is 86.267. It is for 3, 86.267. For 3.5, it is 100.645. Okay, for 3.5 it is 100.645. Then for 4 it is 115.023. Okay, 115.023. Then for 4.5 it is 129.400. This for 4.5 milliamperes of current it is 129.400. And the last one is for 5 milliamperes it is 143.778. Is 143.778. Okay, and after noting these readings, okay, we have to note all these readings in the Excel sheet. We have taken this one, magnetic field B 0.1482. Okay, and the thickness of the strip is 0.1 millimeter. Then we are having these readings, okay, for I and VH values. Then we choose these two columns and we go to the insert option and charts. This is the middle one. We are having this one. Okay. Now we change this one, Hall effect. Hall effect, and we remove these grid lines and we name this axis. Okay, this is Hall current, milliampere. This is Hall voltage. This is in millivolt. Now we change this color to black and we take these values, data labels. more options. Okay, we go to this data labels. Okay, vertical alignment. Like this. These options, label options, x and y values, so below. I will take this one above, and we have to find the slope of this curve. That's why there is no need to this one. Delete, delete. We take the slope of these 2 points. Delete. Okay, 3 and 4. Delete, delete. Okay, as the difference between x coordinates is 1, the difference between the y coordinates gives the slope. Okay, and you this entire curve, and I prefer to change the font to Times New Roman, and I am going to have this one bold letters, and also the okay. Now we can easily have the slope for this one. Okay, and we have to give this one axis. Okay, for axis we change the color to black color, and we increase the weightage to 1.5 pounds, as well as for this one also we change the color to black, and we increase the strength of the line to 1.5. This is how we are going to get this one, and by using this thing we can have this one. Copy this one, so you paste this one in a MS Word. The graph of this one, the slope is given by the difference between these two. It is 115.023. That is, if we subtract 7 from 13, we get 6. Okay, again we are having 11 minus 6. 11 minus 6 means 5, and 9 minus 2, 7, it is 7. Then here we are left with 14. 14 minus 6, that is 8. Then we are having 11 minus 10 minus 8, that is 28.586 is the slope. Then Hall coefficient can be determined by using this one. RH is equal to VHT by IHTB, that is slope into T by P, where we are getting this value as 0.0194 meter cube per coulomb. This is the Hall coefficient for the germanium. Okay, this is how we can find the Hall coefficient of a given material. Yeah.